Welcome! Today, we're tackling a classic orbital mechanics problem that looks way more intimidating than it actually is. If you've ever seen a problem like this and thought, oh no, this is going to be pages of crazy math, then you're in the right place. We're about to uncover a really elegant shortcut that's hidden inside one of the most fundamental laws of physics.
Okay, let's break this down. We've got a planet, it's in an elliptical orbit, its closest point to the sun is r, and its farthest point is r. The question is simple. Find the period. How long does it take to make one full lap? Now, here's the trap. A lot of people immediately start thinking about the planet's speed. It's constantly changing, right? It speeds up when it gets close to the sun, and it slows way down when it's far away. That just screams complicated calculus, doesn't it? Like, you'd have to integrate that changing speed over the entire path.
Well, before you bust out the heavy-duty math, let's check out a hint from the original textbook solution. It gives us this surprising, almost sneaky shortcut that lets us ignore all that complexity.
So get this. The hint tells us to just forget the ellipse, pretend it's a simple, perfect circle, and we'll get the exact same answer for the period. But why? How on earth are we allowed to just swap out the shape like that? This isn't just some random math trick. It's based on a really deep physical principle. And that's the puzzle we're going to solve right now.
And the secret weapon here is Kepler's third law. It basically says an orbit's period, t, is tied directly to this one geometric property called the semi-major axis, a. But the really crucial thing here is what the law doesn't say. See what's missing? There's nothing in there about the orbit's shape, its eccentricity, or the planet's constantly changing speed. Nope. All that matters are these two things, the period, t, and this a thing, the semi-major axis.
And check this out. This is the law in action. You've got Earth and Jupiter, totally different orbits, different speeds, the whole deal. But if you do this one little bit of math, take their period, square it, and then divide by their semi-major axis cubed, boom, you get basically the exact same number. It's like this magic constant for anything orbiting our sun.
Okay, so let's bring this powerful idea back to our problem. To use Kepler's third law, we just need to figure out one thing. What is A, the semi-major axis, for our planet's specific elliptical orbit? That's the only piece of the puzzle we're missing. So, how do we find A when the only two numbers we have are r, the closest point, and r, the farthest point? This might sound a little complicated, but you're about to see that it's actually incredibly simple. All right, just picture the ellipse for a second. The sun isn't in the dead center. It's off to one side, at a point called a focus. So the total width of the orbit, the longest line you can draw across it, is just the farthest distance, r, plus the closest distance, little r. And the semi-major axis? Well, semi just means half, so a is just half of that total length. It's literally just the average of the two distances we started with.
Okay, we've got all the pieces. We have Kepler's law, and we know exactly what the semi-major axis of our ellipse is. Now we can connect the dots and finally see why that mysterious shortcut actually works.
And here it is, the aha moment. On the left, you've got our planet's real orbit. It's an oval, its speed is all over the place. On the right, you've got that simple shortcut circle. They look totally different, right? But look at the one thing they have in common, their semi-major axis. It's exactly the same for both. It's just r plus r divided by 2. And that is everything.
Because what Kepler's third law tells us loud and clear is this. If two orbits around the same star have the same semi-major axis, they absolutely must have the same period. End of story. All that other stuff, the weird shape, the changing speed, it's all just noise. It doesn't affect the one thing we actually care about, which is how long it takes to go around.
So when we take our nice, simple value for A, r plus r divided by 2, and we plug it into the full physical equation for Kepler's law, we get our final answer. Now yeah, this version has the mass of the star, m, and the gravitational constant in it, but look close. The only piece of information we needed about the orbit itself was its semi-major axis. No complicated calculus, no integration, we just sidestepped all of it. So what's the big lesson here? It's that an orbit's year depends on one and only one thing, its semi-major axis, not its shape, not how squished or stretched it is. And the most common pitfall is getting totally lost in the weeds, trying to calculate the varying speeds and the complex geometry. People forget to step back and ask, what's the fundamental law that governs this whole system?
So the next time you face a problem that looks like a total monster, just pause. Remember this ellipse. Before diving into the nitty-gritty, ask yourself, what's the real fundamental law at play here? You might just find a beautifully simple solution hiding there in plain sight. Thanks for joining me on this explainer.